let's try to solve this problem here. So you have a test charge which is Q0, which is positive 5 microcoulomb, and it's placed at point M. So here you have Q0 and it's 5 microcoulomb. And it's 6 cm away from a point charge which is Q as shown in the figure above. So I believe initially Q is situated over here, Q0 is situated over here, which is 6 cm away from Q. And they label this place as point M. Okay, then they say the work required to bring the charge Q0 from M to N is 4 joule. Okay, so this one is work required. They didn't specify it's work done by electric force. They didn't specify work done by electric field. They didn't specify work done by a certain charge. So in this case, this one will be work external. Okay, this one is external, work done by external force. Okay, so let's be clear that everything is clear. Okay, so yeah, so let's write down the charge move from M to N. And for this process here, if you find the work done external to move the charge from M to N, you will be going to find the answer to be equals to 4 joule. Okay, so that's what you know. Okay, so let's expand our idea, what we know about work external based on what we have learned in class. Okay, so we know that work external, if you go from M to N, okay, you know that work external is equals to delta U, which you can further expand it to become Q delta V. Again, we have to be very clear over here. Q here has to be the charge that moves from M to N. So which charge is moving from M to N? Q0 is the charge that is moving from M to N. It's not Q that is moving. Q is stationary. It is Q0 that moves from M to N. So in that case, the charge that moves has to be the charge that we put in here. So in this case, we cannot write Q. It will be incorrect. We have to write it as Q0. Okay, so it will be Q0 multiplied by the potential difference. So potential difference, you have to look at the situation. It's always final minus initial. So final minus initial for this case, the final will be N, the initial will be M. Okay, it's always final minus initial when you have delta V over here. Okay, so final minus initial. Final is N, initial is M. Okay, so that's what you know for now. Okay, so I believe you have a lot of information that you can substitute here at this point. Okay, so it allow us to find something. Let's just put in everything. We know that the external work done by external force is equals to 4 joules, so we can put in here to be 4. And we know that Q0, the charge is 5 microcoulomb, so you can put in 5 microcoulomb over here. So essentially, we have already substituted in everything that we can substitute. Then what's left is Vn minus Vm. Okay, so Vn minus Vm will be equals to 4 divided by this value over here, which is 8.00 times 10 to the power of 5 volt. Okay, so this is Vn minus Vm, but is it what the question asked for? Well, you have to look at the question. What did they ask for? They asked for potential difference between M and N. Okay, so there are a few ways to ask for potential difference. I've gone through it in class actually. So you can let's give an example. You can ask what is the potential difference between A and B. Okay, or sometimes you can say what is the potential difference experienced by a charge by, let's say, Q0, since Q0 is moving, when moving from M to N in this case. Okay, so if you see they ask for potential difference and they state it clearly that it's moving from a certain place to a certain place, in this case, finding the potential difference is actually not difficult. You will just take the final minus the initial. It's always like that. Okay, so the final will be N because you move to N. Sorry. The final will be N, the initial will be M. So this one will be N minus Vm. So this one is clear cut, it's straightforward. Okay, but if you look at example 1 says between A and B. Well, between, the word between doesn't necessarily means you go from a certain place to a certain place. It's just saying that what is the difference between the 2 points. They didn't say where is the starting point, they didn't say where is the ending point. So it's possible that you are moving from A to B. It's also possible that you're moving from B to A. In fact, for this situation, if you look at a few international book, established international book, they are fine with you writing it as VA minus VB, and they are fine with you even writing it as VB minus VA, because they didn't really specify where you go from and where do you arrive at. Okay, so it's not specified. However, if today you are a Malaysian matriculation program student, according to this year's standard, after being discussed among the lecturers all over Malaysia, they have already decided to standardize it in the sense that if they say it's between what and what, it is always the first alphabet that will be the initial position, whereas the second alphabet will be the final position. So in that case, not all of this can be correct anymore. You cannot just assume them to be correct. You have to think like how we think over here. Okay, so let me write it in green. So we are not, let's just say we don't do it this way anymore. What we do is, we will still do it as usual. Delta V is always V final minus V initial. So in this case, final it's B, initial it's A. So in this case, delta V will be equals to VB minus VA. Okay, so the idea is if it's between A and B, the first alphabet that we see between A and B, the first alphabet will be initial position, the second alphabet will be final position. So because potential difference is always final minus initial, so it's VB minus VA in this case. Okay, I'm not saying that the whole world will follow this convention where the first term is initial, the second term is final. In fact, I don't think it's necessary to fix who is initial, who is final. I think I'm okay with it being either positive or negative sign because the word itself doesn't carry any direction from where to where. But since the lecturers has already decided that this is the way to go, we will just follow this convention where the first term is the initial position, the second term is the final position. Okay, so in this case, come back to our question. It says between point M and N, between point M and N. So this one means that M here will be our initial position, whereas N here will be our final position. So in this case, what they're asking for the potential difference between M and N. So potential difference over here will be taking the final, which is Vn, minus the initial, which is Vm. Okay, does it match with what we have calculated here? Yes, that's why the answer will be equals to 8.00 times 10 to the power of 5. Okay, however, if today, I'm not saying that it happens here, but if today the question asks for between N and M, then it's inverted already, right? So right now, N will be initial, M will be final. So in this case, final minus initial will be equals to Vm minus Vn. So in that case, we know that it's the inversion of Vn minus Vm, just flipping off the sign. So the value will be equals to negative 8.00 times 10 to the power of 5. Okay, in this case, this is what the question asked for, of course. Okay, I'm just saying that just in case the question asks for a flip between, okay, N and M, you have to check whether it's the same as what you've calculated here. Because it's different, it's flipped already, you have to add on a sign to flip the sign of the answer that you get previously. Okay, so always be careful when you get your answer. Don't immediately say that it's the answer. Check, is it really what they're asking for, or they are asking for the opposite sign of it? Okay, you have to do the checking by yourself. Okay, next, the value of point charge Q. Okay, so they ask for the Q, what is the point charge over here? So we know that point charge Q here, because of its presence, the surrounding region around Q has an electric potential. Then what happens is Q naught being positioned at M will interact with the electric potential at position M, which is produced by Q. Then as it interacts, it will have an electric potential energy. And because you move it to another position, at this another position, the electric potential is different. So because you are now interacting with the electric potential at N, you will have a different electric potential energy. So there's a change in electric potential energy when you move from M to N. So any change in potential energy means that you actually had there's work done in this situation. Okay, so that's a rough idea of it. So for this case, they're asking for the value of point charge Q. Point charge Q we know that Q is responsible for creating the electric potential that Q naught is interacting with. Okay, Q is the one that is producing the electric field. Q naught is the one moving, so it is the one interacting with the electric field, electric potential at this point. It is the one interacting with the electric potential at this point. So produce, interact. So because it's produced, we will be using the produce equation. So the V produced by VL, we can just write it as Vn minus Vm. Let's don't confuse it. Okay, we can still write it as Vn minus Vm. That's what we have known earlier. But Vn here, which is the electric potential over here, can be found by a spring that we can connect between Q, the one that produces the electric potential, and N, the point that we want to find the electric potential. So this spring here is KQ over R between Q and N. Okay, they call it Rn immediately. Okay, then this will be equals to Vn. Okay, then for position M, the spring is from here to here only. Then this will be Vm. It will be equals to KQ over Rm. Okay, so we know these two positions. We know how to determine their electric potential. So now we can just put in the expression. So this one will be KQ over Rn. This one will be minus KQ over Rm. So we know that Vm minus Vm is 8 times 10 to the power of 5. K, you can factorize it out. Q, you can factorize it out. You are left with 1 over Rn and 1 over Rm. Okay, well, substitution left. 8.00 times 10 to the power of 5. K is 9 times 10 to the power of 9. Q, 1 over Rn. Rn is 10 cm, 0.10. 1 over Rm is 6 cm, 0.06 meter. Okay, so substituting everything and do a calculation, I believe you get Q to be a negative value, which is negative 1.33 times 10 to the power of negative 5 coulomb. So what does it mean? Well, this Q over here is actually a negative charge, whereas this Q naught over here is a positive charge. So they are technically mutually attracted to each other. So if you bring them from M to N, things that attract, you can think of it. Okay, let's keep it slow. Q is a negative charge, as we found here. Q naught is a positive charge. So if it's negative and positive charge, they are opposite sign. Technically, by nature, they should attract. So it means by naturally, they want to be as close to each other. But what happens is, if you bring Q naught to M, you are putting a distance between Q and Q naught, right? So that process itself is like stretching a short spring to a distance of 6 cm. So stretching it stores some amount of electric potential energy already. Okay, but now if you move it from M to N, if you move Q naught from M to N, what happens is you are further stretching the spring. So if you are further stretching the spring, then you store more electric potential energy because you're stretching it further, right? So you store more electric potential energy. So the process of going from M to N, you will see that it stretch more. Okay, stretch more means by your U increases. Okay, so based on the idea that work external is equals to delta U, U increases means delta U is positive, right? So if delta U is positive, that means your work external is positive. So is it true that our work external is positive? Yes, because they say the work external to bring the charge from M to N is 4 joule. It's positive 4 joule, it's not negative 4 joule. So everything makes sense. The sign, everything connects well with each other. So we have roughly see that our answer sort of makes sense. Okay, if today your answer is a positive charge, then that means that Q and Q naught, they are both positive. If they are both positive, they should mutually repel. So they want to get as far away from each other. So if you bring it to M, is you are compressed a long spring to a short distance of 6 cm. You have to compress it very strongly. You compress it very hard until you reach 6 cm. But if you move Q0 from M to N, what happens is you are releasing a bit of the compression just now so that it extends a bit. Okay, previously you compress it a lot, but you release the spring a bit so that it gets longer until you reach 10 cm. So when you're releasing the compression a bit, you're actually reducing the compression. So that means that you are storing less potential energy. So U will be decreases. Okay, then delta U will be negative. Then your work external will be equals to negative. That's what happens if it is a negative charge for Q. Okay, so let's write it down. Okay, if Q is positive, then this is what it means. If Q is negative, you reduce the compression. Reduce compression, because before that it's compressed to a very short spring, but you lengthen it by reducing the compression. So U will decrease. So if U decrease, then you can think of it as delta U is negative. Then in this case, you will know that work external will be equals to negative. Okay, of course we have already checked that. Of course we already determined the answer. The correct answer is the first situation. This is the right one. This is not the right one. Okay, so we are just checking whether the sign is logical or not. Okay, if the sign is positive, you should get work done. Work external is positive. If the sign here is negative, you should get work external is negative. But since work external is positive, then everything match here. This is the situation that we are talking about. Okay, so that's it for this question. Thank you very much.